Today we are going to learn about optimizing memory usage with efficient data structures. You will understand how to choose and implement data structures that optimize memory usage, ensuring scalable and efficient applications. Welcome to this video on optimizing memory usage with efficient data structures. In today's world, where data is growing exponentially, managing memory effectively is crucial for maintaining application scalability and speed. This video will guide you through understanding the memory usage of basic data structures, comparing their efficiency, and exploring techniques to reduce memory overhead. We will delve into case studies of popular applications, discuss trade-offs between time complexity and memory usage, and introduce tools and frameworks for monitoring memory usage. By the end of this video, you'll have the skills to analyze and select data structures that balance memory use and performance.
Arrays are one of the most fundamental data structures, offering a fixed size and contiguous memory allocation. This structure allows for efficient memory access due to predictable data placement. However, the fixed size of arrays can be a drawback, especially when dealing with dynamic datasets that require frequent resizing. Arrays are best utilized in scenarios where the data size is known beforehand and remains relatively constant. Despite their limitations, arrays provide a baseline for memory efficiency, serving as a benchmark for comparing other data structures. Understanding arrays' strengths and weaknesses is essential for optimizing memory usage in various applications. Lists, particularly linked lists, offer dynamic sizing, making them suitable for applications where data sizes vary frequently. However, this flexibility comes with memory overhead due to the pointers required for linking nodes. Linked lists can lead to memory fragmentation, complicating memory management. Despite these challenges, linked lists are invaluable in scenarios requiring frequent insertions and deletions. Comparing lists with arrays highlights the trade-off between flexibility and memory efficiency. By understanding these nuances, developers can make informed decisions on whether lists are the appropriate choice for their specific memory optimization needs.
Trees offer a hierarchical data representation that is highly beneficial for managing structured data, such as databases and file systems. The memory usage of trees depends significantly on their balance. Balanced trees like AVL or red-black trees maintain efficient operations but require additional memory for balance information. Unbalanced trees can lead to inefficiencies in both memory and performance. Trees excel in scenarios requiring efficient search operations, but the trade-offs between performance and memory must be carefully considered. By mastering tree data structures, developers can optimize memory usage while ensuring high-performance data handling.
Choosing the right data structure is crucial for optimizing memory usage. Arrays, lists, and trees each have distinct memory footprints, influencing their applicability in different scenarios. While arrays offer minimal overhead, their lack of flexibility can hinder scalability. Lists provide dynamic sizing at the cost of additional memory for pointers, whereas trees balance memory usage and performance through hierarchical organization. The decision on which structure to use should consider both memory efficiency and speed requirements. By comparing these structures, developers can make informed choices that enhance application scalability and performance. Reducing memory overhead is vital for optimizing memory usage. Techniques such as memory pooling and strategic allocation can significantly enhance memory efficiency. Compression techniques enable data storage in a reduced format, saving memory without compromising data integrity. Efficient memory layout planning ensures minimal memory wastage, while avoiding memory leaks is crucial for sustainable memory management. By examining case studies of optimized applications, developers can gain insights into effective memory reduction strategies, fostering more scalable and efficient software solutions. Exploring real-world case studies provides valuable insights into memory optimization strategies. Leading applications like Google Chrome and Facebook have employed innovative techniques to manage memory efficiently. These industry leaders emphasize the importance of balancing memory usage with performance demands, utilizing memory profiling tools for continuous improvement. By understanding the methodologies applied in large-scale applications, developers can adopt proven strategies that enhance their software's scalability and efficiency. Learning from these examples fosters a deeper comprehension of effective memory management in practice. Trade-offs between time complexity and memory usage are pivotal in data structure and algorithm design. Understanding these trade-offs aids developers in making informed decisions that balance speed and memory efficiency. While some structures offer faster operations, they might consume more memory, and vice versa. Examples of common trade-offs include choosing between hash tables and arrays or AVL trees and red-black trees. By grasping these concepts, developers can follow guidelines for selecting the most suitable data structures and algorithms, ensuring optimal application performance and memory management. Monitoring memory usage is crucial for optimizing applications. Tools like Valgrind, JProfiler, and Visual VM provide comprehensive memory analysis, offering insights into memory allocation and usage patterns. These frameworks integrate seamlessly with development environments, enabling continuous monitoring and profiling. The benefits of such tools include identifying memory leaks, optimizing memory allocation, and improving overall application performance. By utilizing these tools, developers can gain a deeper understanding of their application's memory dynamics, facilitating effective memory management and optimization. Memory profiling is an essential technique for optimizing data structures. It involves analyzing memory usage patterns to identify bottlenecks and inefficiencies. Profiling techniques enable developers to optimize data structures, ensuring they use memory efficiently. A case study of profiling in action highlights the practical application of these techniques, demonstrating their impact on performance improvement. By incorporating continuous optimization strategies, developers can maintain optimal memory usage, enhancing their application's scalability and efficiency. Understanding and applying memory profiling techniques is a critical skill for effective memory management.
Emerging trends in memory-efficient data structures are shaping the future of software development. Innovative designs, such as succinct data structures and cache-friendly algorithms, are pushing the boundaries of memory efficiency. Hardware advancements, including increased memory capacity and faster processing speeds, influence these trends, enabling more sophisticated memory management techniques. As technology evolves, developers must adapt to these changes, embracing new methodologies and tools. By staying informed about emerging trends, developers can ensure their applications remain scalable and efficient, leveraging cutting-edge memory optimization strategies.
In conclusion, optimizing memory usage through efficient data structures is paramount for developing scalable and high-performance applications. We explored the memory usage of basic data structures, compared their efficiency, and examined techniques for reducing memory overhead. You now possess the skills to analyze and select data structures that balance memory use and performance. As you continue your learning journey, I encourage you to explore further, staying abreast of emerging trends and technologies. Effective memory management is a valuable skill that will enhance your development capabilities, fostering more efficient and scalable software solutions.